Okay, I think we are ready to begin. So hello, everyone. Welcome to the next Warsaw University Astronomical Observatory Tuesday seminars. And today our speaker is actually from Warsaw. So Oliver Newton is a postdoc working at the Center for Theoretical Physics, Polish Academy of Sciences, but unfortunately he couldn't join us today in real life, but we can still fix that later. So Oliver, he's from UK and he studied in Warwick and then Durham, and then did his postdocs in France and Liverpool. And now, as I said, he's working in Warsaw. And so that's gonna be a theoretical talk. So I warned Oliver to be gentle on us. But that's going to be about dark matter, so some topic we are all interested in. So, Oliver, the floor is yours.
Thank you very much. Thank you for the introduction and inviting me along to give the talk, even though I couldn't be there in person today. And you summarised my introduction already, so I suppose by way of introduction, just to say that a lot of this work that I'll kind of discuss, that I'll discuss today, was carried out while I was in France. So the position in Liverpool was quite short. So I'm just getting going with things in Warsaw. So hopefully maybe in another year's time, I can come back with something a bit different from my time in Warsaw, maybe. Yes, as the title says, today I'll talk a bit about using constrained simulations, which I'll explain what these are, to explore the local group. And hopefully I'll convince you all that working on the small scale end of this of things is an interesting field to look at. So if this will advance, there we go. So by way of an overview, I thought I would kick things off, as I say, by trying to convince you that working at the small scale is an interesting field to study. And I'll introduce you to the constrained simulations themselves. They're called HESTIA. They're a relatively new suite of simulations that were published, I think, about 2 years ago now. So they are relatively new. And then I'll talk about some of the first results from HESTIA that I was working on, both while I was in France, and then some work that is current that hopefully will be published soon. So hence the warning sign. You know, it's not published yet, but forthcoming and in progress. So yes, to get going with this, why are small scales interesting? I should probably define what I mean by small scales. In this context, as density fluctuations in the universe evolve through time, when I say small scales, I mean that density fluctuations of different masses and different sizes become coupled. So they no longer evolve independently like you would expect in the large scale regime. And practically what this means is that local dynamics and interactions between objects become much more important to describe how they're going to evolve through time. So to study this in this regime, numerical simulations have become an essential tool to understand these dynamics and study the behavior of cosmological models in this regime. They've already been used very successfully on large scales to test different theories, and indeed they've helped in the rise of lambda CDM, for example, as the standard cosmological model, and it's helped to demonstrate several successes of this model, for example, in explaining anisotropies in the cosmic microwave background, or in predicting the location of the BAO peak, statistics relating to weak gravitational lensing, and the polarization of the CMB. So this works very well on large scales, but if we start to push dark matter only simulations down to smaller and smaller masses, we start to see the emergence of some discrepancies, particularly at dwarf galaxy mass scales, that start to challenge the lambda CDM hegemony. So I thought I would talk through 3 of these. There are many more, but just to set the scene a little bit about, again, looking at why we study the small scale. So on the left-hand side, I have a plot of basically the number of galaxies, I think normalized by volume, as a function of, in this case, circular velocity, or you can take that as a proxy for mass. And if you look at the galaxy population around the Milky Way and M31, or similar sized halos, which we have represented here by these black triangles and error bars, and compare that with, you ask the same question of the dark matter-only simulations from lambda CDM or CDM, you find that at low masses you get quite a large discrepancy, whereas you might have a few hundred in small galaxies in observations. The simulations themselves are predicting 1,000 or so. So this discrepancy, discovered I think 20 odd years ago, became known as the missing satellite problem. In the middle, we have a slightly more recent, well, somewhat more recent update to this second problem, which is if you plot the rotation curves of low mass galaxies, again, these observations are plotted here with these points, and you compare that with the circular velocity curves of a similarly sized dark matter halo from the similar mass dark matter halo from simulations, you find that the observations suggest that the galaxies there have a shallower density profile or a more chord profile than the very cuspy NFW-like halos from simulations. And so this discrepancy became known as the cusp core problem. And the final one, which I think is somewhat related with this, the cusp core problem, if you take the peak in the circular velocity curve, which is what we've done for observed satellites and low mass galaxies near us with these points down here, and compare those with some of the most massive subhalos from simulations, or the circular velocity profiles of some of the most massive subhalos from simulations, which are what these grey lines are, then the observational data suggests that these galaxies sit in not the most massive subhalos, but the next set down, which is a bit puzzling because taking these subhalos from the simulations, these are some of the most massive subhalos in the simulation, and were basically picked to sit above a mass threshold where we would expect they would successfully accrete coal gas, form stars, and be relatively unaffected by things like reionization and so on. And so naively, you would say that they're too big to fail to form galaxies, and yet we find this discrepancy between the simulations and observations. So all of this and many other problems contributed to what's become known as the small-scale challenges to lambda CDM. But they originate by comparing dark matter-only simulations with these observations. Obviously, that's a gross oversimplification, given that the rich interactions between baryons, so responsible for galaxy formation, are not included in these simulations, and so perhaps it's not so surprising that in hindsight, it's not so surprising that we discovered these discrepancies. Since then, we found that even including relatively simple models of baryonic physics can start to alleviate some of the tensions that seemingly were model killers. The moment you start to add a model for galaxy formation or the interactions of baryons, it starts to relieve some of these. And so for the three problems I've just described, whereas before they were serious issues that spurred on a lot of interest and research, now they're starting to move into a much lower category of tension, if you like. They're less strongly in tension with observations. And so this comes from a review article that was published this year, led by Laura Sales, Andrew Wetzel, and Azi Fatahi, and they were trying to summarize the literature around including relatively simple models of baryons in our simulations to try to understand, where things sit and where the consensus lies with these challenges to lambda CDM. So while most of these challenges, I think, now are being explained away by improving models, there are some that still pose a bit of a challenge, and I'll draw attention to one in particular, which is the satellite planes, and this refers to the configuration of satellite galaxies around the Milky Way and M31 on scales much larger than you would expect any baryonic physics to have effects. So you can't explain necessarily these planes away by just including a model of baryonic physics. So to try and explain what I mean, if you look at the galaxies of the Milky Way on the left and Andromeda on the right, you can fit a plane through these galaxies, and relative to the screen, they've been marked on. So I modified these from a review article from last year. I've marked these on such that galaxies that are approaching us have a downward facing or blue colored arrow. Those that are receding from us have an upward facing or red arrow, and I should say receding relative to the screen that we're looking at. So while forming planes, you can do that in a dark matter only halo, for example. What makes these particular planes interesting is that they seem to be kinematically coherent, and that's been confirmed by observations from Gaia DR3, I think, and by pandas as well. And that becomes a little bit harder to reconcile. Why would they be in kinematically coherent planes? Do we expect to find such kinematically coherent planes in lambda CDM? How common would they be? So you can ask this question, go into the simulations and ask how many pairs of halos, of Milky Way mass halos, have similarly thin kinematically coherent planes with at least as many satellites as we see in the observations. And the exact number that you get out is a little bit under debate, but generally it will sit somewhere in the ballpark in the range of 0.1% to 10% of paired halo systems will both have these similarly thin and kinematically coherent planes. So even though that number is debated, we can agree, I think, that suggests that the local group, our local group, is a bit unusual. And that's problematic because we use the Milky Way sometimes and M31 as, and indeed the galaxies, the lower mass galaxies that are in the local group, as templates with which to compare populations further afield. We can study them better, they're closer. So the question now is, well, if our local group is unusual, how much can we trust doing this comparison with other populations? And can we? Is it a valid thing to do? And that spurred a lot of interest in trying to construct what we're calling constrained simulations, which aim to embed a relatively realistic local group in slightly larger scale structure that matches the observations. And it allows us to ask questions like how the local environment affects either galaxy formation or structure formation in our patch of the universe. So as I say, we aim to produce local group analogues in simulations that are consistent with the larger scale structure. And we do this by building initial conditions using a Bayesian reconstruction approach with the prior that, well, in this case, the one for the simulations I'm going to introduce, with the prior that lambda CDM is the right model. And we can use two different types of data. I say different types of data, but we can use two types of observation to constrain the initial conditions. We can either use galaxy redshifts from redshift surveys, or we can infer the peculiar velocity field from other observations, redshifts and luminosities, to constrain our initial conditions so that we get these local groups, redshift 0, that do a reasonably good job of matching what we see. So HESTIA, the simulations I'm about to introduce, use the second set. We use peculiar velocity field to set the initial conditions, because the redshifts alone have poorer resolution, and so this is why the peculiar velocities lead to poorer resolution initial conditions. So the peculiar velocities are favoured. So HESTIA itself, classic astronomy acronym, stands for High Resolution Environmental Simulations of the Immediate Area. As I say, it was published in 2020, and as mentioned, is the goal with constrained simulations. The aim is to reproduce some major local gravitational sources that are local to us. So, for example, one of the key criteria for selecting HESTIA local group candidates was that we produced a Virgo-like and similar mass cluster in about the right place relative to the local group analog. So there are 13 simulations in total, of which 3 of them are resimulated at what we call high resolution, which in this, in my language, simulation language, means that you have a dark matter particle mass of about 10 to the 5 solar masses and a gas mass of 2 times 10 to the 4. So something to bear in mind as we're going through some of these results that are about to come up. So if we look at this, I don't know how well this will come through Zoom. I think in the past I've tried to show this and it's been a bit laggy, but this is a rendering of one of the simulations, high resolution simulations at redshift 0. I think it's showing gas density. It might be colored by temperature. I can't quite remember, but and so you have the 2 host halos in the center, the Milky Way analog and the M31 analog. And you can see you have lots of lower mass galaxies floating around in the background and in what we're calling the field, or outside of the virial radii of those host halos, dotted all around. So this is what we end up with. We get a reasonably good outcome for the simulations that we have in terms of their similarity to our own local group. So I'll start going through the results. The first one, which I glossed over, I'll introduce you to a population of what we're calling Hermeian halos that sit in the intra-host halo space, or intra-host galaxy space of the local group. And they are, well, I'll demonstrate. They are low mass galaxies that have passed through the Milky Way and M31 and have disappeared out into the field by redshift 0. So it's a very simple definition. We were looking at something else when we were trying to trace back evolutionary histories of the galaxies through the simulations, and just noticed that there was this very, very small population of halos that managed to essentially fly straight through the 2 hosts, which I don't think any of us were really expecting to find, although in principle it's perhaps not unexpected that you could have these objects. But I think we were just surprised that anything was able to survive and head back out into the field at quite large distances by redshift 0. So we find them in all 3 high resolution simulations. They don't count for a very large proportion of the field halo population, less than or around 1%. And most of them are dark at redshift 0, so they don't have gas, they don't have baryons, at least at the level that we can resolve in the simulations. But we do find that 4 of them somehow managed to hang on to their galaxies, mainly the stars, not so much the gas, all the way through to redshift 0. So in principle, if you could find a way to distinguish these from other galaxies, you could go out and ask, do we have a similar population in our own local group? And so we set out to try and understand a little bit about this population and whether it could be useful for anything, basically. So here I've just plotted the the distances of the Hermeian halos relative to each of the hosts. So the Milky Way on the left and M31 on the right as a function of look-back time. So look-back time of 0 is the present day, and you're heading back further and further as you go to the right. So the eagle-eyed among you might infer that there seems to be one group that comes in via the M31 before heading on over to the Milky Way. There's also a second smaller collection of halos that go in the opposite directions. They enter or pass through the Milky Way first before flying out and passing through the halo of M31. And the dotted line here just represents the virial radius of those host halos. And I should mention as well this funny artifact here. So it's a nice example of some of the perhaps the foibles of working with these simulations. When we try to identify these halos and their main progenitors in the simulations, sometimes when you have a lot of halos clustered together, you can end up misidentifying which one is the main host or the main progenitor of a given halo at a previous time step or previous snapshot. And so basically this has happened for M31 here. Its halo has been misidentified with another one, and so the center of the halo jumps very slightly, and so you get this wiggle, apparent wiggle in the trajectories of the halos. This is an artifact. It doesn't actually affect our results, so I haven't corrected it, but left it in as a discussion point. So the grey halo, the grey lines, thin lines are the dark Hermeians, and the thicker lines and markers indicate the four that have galaxies that retain stars, all the way through to redshift 0. So it's perhaps a bit easier to see in projection, looking at the trajectories. So I've taken the same scheme of representation as before and marked the start of their trajectories with these unfilled squares. So we're basically progressing up from the bottom right to the top left, and this is just a projection in simulation coordinates basically. And it's a bit easy to see that you have these two sets of halos that travel in opposite directions, and you have a large group infall towards M31 first that then travels on over to the Milky Way. And so this means that at redshift 0, most of the group end up on the far side of the Milky Way analog, and not so many on the other side of M31. So if you were to position yourself at the center of the local group, or the midpoint between the Milky Way and M31, and look at the angular distribution of the different galaxies, different populations of galaxies and halos, you would end up with a plot a bit like this. So here, in this coordinate system, if you like, the M31 analog is at 0 degrees, and the Milky Way is at 180 degrees. So that's our kind of viewing angle, if you like, from the center, the midpoint of those two halos. And I've plotted out what I've called field halos. So these are halos that didn't interact at all with M31 or the Milky Way. I've put on a population of backsplash halos. So these just hang around the Milky Way or M31, interacting with it, but they don't travel anywhere. And then you have the Hermeian halos. So these are the ones that interact with both and head out into the local group. And you see this skew in the distribution of the Hermeians, as expected because of that group infall. But you also see a skew in the distribution of backsplash halos. And this arises because of the addition of several more backsplash halos by the group to M31 on its initial infall. So this is a related signal, I suppose. The two signals are related, and it's not a dependence. If you strip out the differences in halo mass, for example, it's not a dependence on halo mass. This signal exists despite that. So if you were to project these onto the sky again, sitting at the privileged position at the midpoint of the local group. So plotting the Milky Way and M31 at plus or minus 90 degrees here. This is the kind of distribution you would see if you could see all of the Hermeian halos. They sit sort of along the line connecting the Milky Way and M31, or very slightly offset from it. And so, at least for the geometric properties of these populations, the hope is that at least we can try to use this to go and search to see if we can find these objects. But I think perhaps more interesting is, or would be more interesting, is what properties do these objects have, and can we make use of them in a scientifically useful way? So this is a little bit busy, but I'll try to talk through it. So again, I plotted the different populations of galaxies from the HESTIA suite on this figure, and it's plotting the maximum circular velocity of the halos versus their mass. And I've broken up the backsplash population based on the number of pericentric passages they experience, 1 or 2. So naively, you would expect that a backsplash halo that has had 2 pericentric passages would have properties similar to the Hermeians, which have experienced 2 passages with 2 different halos. And this is what we seem to see. So the reason we've plotted this out is because at fixed mass, halos that have a higher circular velocity have a higher concentration relative to those with lower circular velocity at fixed mass. So you can see that the field halos sit on this black line, which is the concentration mass relation from cold dark matter. It's been well studied. It's been well studied. They sit nicely on this, as you would expect. Then a slightly more concentrated set of halos. You have the M=1 backsplash halos. These are slightly more concentrated than the standard lambda CDM field halos. And then at the top end, you have the Hermeians and M=2 backsplash halos that on average are about twice as concentrated as the field halos that don't interact with the 2 hosts. So this is interesting because we can potentially use more concentrated halos as useful targets to detect any signals of dark matter annihilation. And so this is where we start to get into some more scientific useful properties of these objects. So when you are looking at objects and trying to calculate what you might expect from its dark matter annihilation, the photon flux you would expect to get from it, you can break up into 2 parts. There's a particle physics part, which basically encodes the information specific to the dark matter particle itself. It could be its mass, its interaction cross-section, and so on. Things that we don't know a priori. And then you also have the second part, the astrophysical J factor, which is more useful to us as astronomers, that it encodes things that are astronomically relevant, such as the distribution of that dark matter. And basically it tells you how much dark matter you have in some opening angle along the line of sight to your object, and acts as a scaling term for the photon flux from the particle physics component. So basically, higher J factor means you'll get more flux from a given object compared to another object with lower J factor. We find, so we've calculated this, and I've plotted this as a function of distance. As you might expect, distance will affect the size of the J factor, as well as the mass of the object and its concentration. As you can see, so this shows all of the J factors we've calculated for the Hermeian population, and I've circled the 4 galaxies, the most massive objects in the Hermeian sample. And we find that the maximum of these J factors is comparable to most dwarf satellite galaxies around the Milky Way, for example, and galaxy clusters. However, it's below the most promising of nearby targets, for example, the Draco dwarf galaxy that sits near the Milky Way. So individually, we don't expect the Hermeian halos to be particularly useful compared to the best-in-class objects. but potentially we could make use of the size of this population to get some useful constraints. And so in conversation with my gamma ray astronomer colleagues, they've said that if we could take this population, and most of the sources appear to be point-like in our observations, then we could use some kind of combined likelihood analysis to improve the detectability of the dark matter signal. And so here I've plotted the spatial, or the angular extent rather, of the photon emission region from each of the Hermeians. Well, the J factor is a function of this, and color-coded them by concentration. So as you might expect, the more concentrated halos have a much smaller angular size compared to those that are less concentrated. I've also added on the point spread function from Fermi-Lat. Gamma rays, you can see that most lie to the left of this, so most of them would appear as point-like, so would be valuable for this kind of analysis. And even future telescopes like Cherenkov telescope array or better telescopes that will have better angular resolution, most of the population would still appear to be point-like in this, so it could still be used to improve the dark matter signal detectability. So potential utility there. And the last thing I want to just mention on this before moving on to the second part of the results that I'll present today is that the Hermeians themselves act as conduits of matter transfer, both dark matter, gas and stars, between M31 and the Milky Way. We see this in the simulations, although we are at the limits of the resolution of the simulations, so there's a limit really to what we can say about this. But we do see that some of the Hermeian galaxies do come in, collect gas from the halo of M31, travel the distance between the two in the local group, and deposit it in the Milky Way, at the same time triggering an enhancement in the star formation rates. So the Hermeians, via the transfer of material between the two host halos, act as something of a source of chemical pollution, we argue, in the host halos themselves. So they really are true cosmic messengers between the Milky Way and M31. So to wrap this section up, as I say before moving on, Hermeian halos are not especially common. We've had a follow-up paper that we've just put up on archive to submit, where we study a larger sample of local group, like objects in a dark matter only simulation, just to look at how different properties of the local group pair can affect the size of the population. Generally, they account for about 1 or 2% of the total field halo population. But they are more concentrated than other field halos, which could make them useful as potential sources of dark matter annihilation signals. And I think perhaps, at least from my perspective at the moment, is perhaps most interestingly, the transfer of material that they can carry out between the two primary or host halos, the Milky Way and M31, could maybe leave some kind of fingerprint or some source of pollution in those two that could be a signal of their presence in the past. They're also very anisotropically distributed at large distances from the Milky Way and M31 in the local group, which hopefully makes them slightly easier to find because of this very constrained spatial distribution. So I'll keep going on unless anyone has any burning questions, but I'm happy to wait till the end for those. I'll carry straight on to the second result that we get from HESTIA, which is studying or trying to study ultra-diffuse galaxies in the local group. So again, little warning symbol just to say it's not published yet. We're still working on it actively, although it's near enough there that we're ready to start talking about it and garnering and getting feedback from people. When I say ultra-diffuse galaxy, what do I mean? Well, this is an example of perhaps one of the most famous ultra-diffuse galaxies of recent times, discovered by Peter van Dokkum in 2018. This is NGC 1052 DF2, the galaxy without dark matter. And you can see it's a very diffuse object, just a bit of a smudge on the screen, very hard to detect. So being slightly more rigorous about this, for our purposes, they are what I would call classically bright galaxies, by which I mean they have stellar masses and absolute magnitudes comparable with the classical satellite galaxies of the Milky Way. But where they differ is that their sizes are approaching those of L-star galaxies, which gives them very low surface brightness. And as I say, makes them very difficult to find. But they're interesting because their very diffuse nature means that they could be useful as probes of dark matter. You clear out most of the baryons from the center, you get a cleaner signal from the dark matter that is less confused by having to explain difficult baryonic physics that we don't have a good handle on yet. So far, hundreds have been discovered in various galaxy clusters, but it's very likely that the census is incomplete. And so we argue that there are some good prospects for discoveries in the nearby universe, and we just need to go looking for them. So the first question to ask in HESTIA is, or at least in the local group, is how many have we seen so far? And at least according to our selection criteria that we use, 8 galaxies satisfy this, 6 of which belong or are satellites of variously M31 or the Milky Way, and only 2 sit out in the field. These what we argue are pristine, would-be pristine objects that haven't had many interactions with the host halos, and so could be useful for these kinds of dark matter studies. So it's unclear at the moment whether we expect to find very few in the local group, or if we just need to do a better job at searching for them. And so we tried to answer this question with HESTIA, and it's work I'm carrying out at the moment, or nearly completed at the moment, with Ariana De Cintio and her PhD student Salvador Cardona-Barrero, and Noam Libeskind, who is the PI for the HESTIA project. So in HESTIA, we use a set of selection criteria that have been published, or a modified set of selection criteria that are in the literature from 2017. Basically, we want galaxies that have stellar masses less than about 10 to the 9 solar masses, effective radii, half-light radii greater than 1 kiloparsec, and a surface brightness that is fainter than 24 magnitude per square arc second. So if we apply these criteria plus an additional quality cut, so we want to select objects from the simulations that have enough star particles that we can reliably calculate these other quantities, the effective radius and the effective surface brightness. So this is why we have a 50 star particle cut as well. If we apply these criteria to the simulations, the 3 high resolution simulations, we find a sample of between 20 to 40 of these UDG candidates, or UDGs, in the simulations, which is quite a few given that we have only seen 2 confirmed so far in the field, in the local group. So taking one of those well, arbitrarily, this is where we expect to find them. So this is courtesy of Salvador. We circle all of the UDGs in this particular simulation, most of which cluster around the 2 primary halos. But we also find some UDGs further out. And if you look at this in 3D, and admittedly by eye, but they sit in sort of the filaments and sheets that feed the local group, and where you expect to find, I suppose, galaxies forming in any case. So plotting this out in the cumulative distribution as a function of distance from the Milky Way analog, this is what we get. So the dotted line here is the full selection of field galaxies that in the same kind of stellar mass range that we're drawing the UDGs from. The UDGs that we find in the simulations are these solid lines down here, and for comparison, we've overlaid the set of observed field galaxies that have so far been observed. So this is an incomplete census at the moment. And it sits down here represented by these dotted lines and error bars. And you can see that around 800, well, it's a little bit hard to see, but the signal is there, around 800 kiloparsecs from the Milky Way. It looks like the population increases more rapidly, and that's just a function of us excluding the central volumes around the Milky Way and M31 analogues. So we're not counting UDGs found in those volumes. That's why you get this kind of behavior. If you look across the entire field halo population, the UDGs in HESTIA seem to account for about half. Doesn't quite stay constant, it decreases with radius, but about half of all of the field UDGs in the stellar mass range, field galaxies in the stellar mass range, are UDGs, which is consistent with some previous work that's been done in different simulations by others. So that's how many we expect to find. The question really is, how many do we expect to detect? So here I started off looking very crudely at the absolute V-band magnitudes, luminosity functions of the UDGs, renormalized to the total number in the simulation. Not sure where the legend's gone on that one, but basically the different colors represent 3 different simulations. And I've applied surface brightness cuts in the R-band for 3 different surveys, the SDSS, DES, and SST. So the SDSS, you have these dotted lines here. Dark energy survey, you have dashed lines, so you're recovering a larger fraction of the population. And for LSST, this actually sits behind these solid lines, which represent the full total population. So basically what we conclude from this rough cut is that SDSS should see in the ballpark of about 70, 80 maybe % of the total UDG population. Dark energy survey in principle should be able to see about 90%, and LSST should be able to see the entire population. Of course, this is a simple cut. There's also an apparent magnitude cut to consider. So if we look at the apparent magnitudes of the UDGs relative both to observers in the Milky Way and M31 analogues, I've marked on the apparent magnitude cuts for the relevant surveys at the top. This implies that you would see almost all the population in these surveys. And so what this is telling us, these 2 plots together, is telling us really that we're limited most strongly by the diffuse nature of these UDGs for their likely detectability in the different surveys. Now, these are crude estimates or crude cuts. We want to be a little bit more rigorous in making a prediction for how many we expect to find in observations. And so we attempted to create mock luminosity functions, mock observations for SDSS, using a more detailed characterization of the detectability of the survey response function for SDSS that was published in 2008 by Sergei Kovasov and his group. So using this, we calculate the detectability of each UDG in our mock observation, and using that as a probability of detection, we can randomly choose UDGs that are detected. And for each Milky Way or each primary halo, post halo, we produce 10,000 mock SDSS observations across the sky to try and generate a luminosity function and the sort of likely scatter that we would expect to find around it. So we're doing this in the 3 simulations. Across the 3, we find somewhere in the region of 5 to 11 UDGs in the mock SDSS observations. with quite a large scatter. These are the 68%. These shaded regions represent 68% confidence limits on the luminosity functions of the Milky Way analog. So there's some scatter here, part of which is due to differences in the masses of the three local groups. So I think 3711, for example, has a mass of about within the volume of, I think, 0.7 times 10 to the 13 solar masses, whereas 918 has 1.2 or 1.3 times 10 to the 13. The mass of the local group is known, has been shown to affect the number of satellite or galaxies you expect to find. So rescaling these luminosity functions to a common local group mass of 8 times 10 to the 12 solar masses, which we think is reasonable from various observations of the timing argument and some extrapolation to larger radii. We expect to find within 2.5 megaparsecs of the local group about 6 field UDGs that are in principle discoverable in SDSS data. And so we argue that you just need to go back with and look for these objects, perhaps finer tooth comb, and they should be there waiting to be found with follow-up analyses. So key points to take away from this: we've shown that UDGs, at least in HESTIA with the galaxy formation models that it employs, UDGs can form in the field of the local group, and we expect to find quite a few in the field, certainly more than have been found so far. As many as half of the field galaxies in this kind of stellar mass range will be UDGs, and beyond the virial radii of the two, the Milky Way and M31, you'll find them sitting along the filaments and sheets that feed the local group. When LSST is operational, it should detect basically all of the UDGs within 2.5 megaparsecs in its field of view. But within SDSS data that's already been taken, we expect that there are around 6 field UDGs that could be discoverable, with some assumption on the mass of the local group. So we're following up this work looking at formation mechanisms of the UDGs, which is an outstanding area of research within the field that hasn't reached consensus. There are several proposed ideas, but still far from reaching agreement. And that's being led by Salvador. So hopefully that will be coming out at some point in the next year. So brings me to the end of this bit of a whirlwind through some of the simulations that we have run and some of the either results or the forthcoming results that we've done. So I'll leave it there and open things up for any questions if you have any. Thank you very much.
Thank you very much. Right, I let Milena lead the questions from the...
Yeah, thank you. Are we unmuted? Yeah, we are, I guess. So thank you very much, Olivier. Why do we call Hermeian halos Hermeian? So
this comes from the ancient Greek god Hermes. Have a nice slide actually here. So from ancient Greek mythology, he actually was god of travelers and wayfarers and presided over the crossing of thresholds and boundaries. But the other nice tie-in with Hestia is that he was a relation of the goddess Hestia, and they were often invoked in tandem during times of transition and change. So it fitted quite nicely to describe these halos that traveled through the local group and the Milky Way and M31.
It's cool, thank you. And thanks for additional slides. So do we have any questions here, the audience? Anyone? Maya? Maybe.
Yes, thank you. So I have a question. Since we expect more ultra-diffuse galaxies to be around in our local group, are you aware of any observational biases that would cause us to miss them?
I didn't quite catch the very start of the question.
Okay.
One second. No.
Okay, hello, can you hear me better now?
I think so, yeah.
Okay, so since I understood that we expect more UDGs to be around, are you aware of any observational biases that would cause us to miss them?
Well, I think part of the reason we haven't really found many is that for some of these large surveys, we haven't found, or at least we haven't attempted, I don't think, to search for such diffuse objects. The main thing is diffuseness. I'm not sure how. I was asked a semi-related question about the color space of the different surveys. I'm not sure how that will map to the UDGs. There are different populations of UDGs in HESTIA that we've found. Some are bluer and some are redder, but I don't know how that compares with, you know, the surveys themselves, and whether that would cause them to drop out of detectability, for example. So it's a yeah, still a relatively simple mocking procedure that we've done, but I think maybe it's a starting point that perhaps will encourage others to give it a try, or go back and see if we've gotten anywhere close with these predictions, whether we can pull anything out.
Okay, thank you.
Any more questions? Anyone on Zoom would like to ask a question? Łukasz, please.
Yes. So the Hermeians, they look fascinating, but so they get large velocities, I guess, right? And I assume that's one passage, or they just you know, visit each of the galaxies and then they are kicked out of the local group. And another question is related to the resolution, because you said that 10 to the 5th is your mass resolution, and you see those objects. So what would happen if you went one order of magnitude lower? Do you expect to see, you know, hundreds of those Hermeians, or you don't expect to see any?
I think so. Yeah. First point, I don't have any plots with me, unfortunately, with the velocities, but basically, I think most are on the trajectory that would, if they're not going to, I can't remember whether they were gravitationally bound in the end, but they're definitely still on an outbound trajectory at redshift 0 in the 3 simulations that we look at in HESTIA. As I say, I'm not sure whether they are unbound, whether they would just keep going or eventually slow down and come back in. And the second question, I think you would find more low mass objects. So if you can try and do the same, the reverse process, and apply a larger cut in mass of Hermeians that you believe you've detected in these simulations, and the mass function appears to follow the same mass function as the field galaxies and the backsplash galaxies, for example. So if we had a higher resolution simulation, I think we would expect to see more, but currently we're missing that, unfortunately. So, but that would be my expectation, that there would be more to be
if you went
found.
even lower, you know, I mean, like to 10 to the 3 or even 10 to the 2, that would be, you know, something very interesting if there is loads of those, you know, 100 solar mass compact halos traveling between, you know, being shoot between 2 galaxies, right?
I suppose at some point there would be, you know, some very low mass halos might not survive, so that would be an interesting question to ask, like, where is that turnover point? Unfortunately, if we were going to answer that question, we would go back to dark matter only simulations, and we'd get rid of the baryon aspect that HESTIA is useful for, because at the moment it would be too computationally prohibitive to keep the baryonic component in the simulations. It may change, but probably not in the next 5 or 10 years at the kind of resolutions you were suggesting there, in the size of some simulation box that we would need to simulate. So yes, that would be an interesting follow-up, I think.
Great, thank you.
So I was wondering, because recently there were some fundings about our Milky Way halo, like a stellar shape of our halo is more like tilted or Zeppelin shape or rugby ball or something like this. And does it affect anyhow your results, this very, very local perspective? Because it also affects the dark matter shape halo, as far as I understand, right?
Yes. I can't answer that question. I don't know. One of the 3 local group analogues that we have, so these high resolution simulations, has a LMC-like analog, which would pull the halo shape around, and whether that also affects the accretion of these Hermeian halos, I'm not sure. So that is in our sample of 3, but we have a small sample, so I would hesitate to draw any strong conclusions from that. But I imagine it could. I mean, we see that the shape of the dark matter halo affects things like stellar streams and so on in other studies that have been done. So I would be surprised if it didn't also affect some of these results as well. But we might need to have a slightly higher resolution simulation than we have here before we see any strong effects, as well as more. We could always do with more simulations.
Any more questions here? Zoom.
I just have a quick follow-up maybe. So you said you only found 3 simulations which looked similar to our local group. So how many have you had to generate and throw away, which were you were just trying and seeing how close it resembles our local group?
So there are 13 in the suite, but only 3 have been resimulated at really high resolution, which are the ones that we use. It turned out that even though we were using relatively modern codes, even then, doing this very high resolution, but still not, it's not the best of resolutions, but still really relatively high resolution in that volume, took a lot longer to run than expected. So that's why we only have 3 high resolution runs instead of 13. But there is a high, so stepping back a little bit, there is quite a high rejection rate for the local groups. I think there are about 1,000 runs done at very low resolution, dark matter only runs. And from that, you start applying different selection criteria. So I can actually show which way is it. Here we go. So you can actually, this is the full set of selection criteria that you used. You need to have a Virgo cluster mass, halo somewhere nearby. You need to satisfy lots of criteria about the halo masses of the Milky Way and M31, their separation and so on. And so basically, for each one of these criteria you apply, you start cutting away more and more of that initial sample of 1,000. So even though we're producing analogues that are similar, they're still, we still have a lot of wastage at this point with the approach, unfortunately. But it's a more efficient approach than selecting randomly from a large simulation box, for example.
Okay, thank you.
Thank you. I think that was the last question. So let's thank our speaker again. And thank you very much, Oliver, and hopefully see you in person one day in Warsaw Observatory. Feel welcome. So thank you very much, and see you next week.